Okay, now we try to share. I want to share this. Okay.
Ready?
Okay, great. I think it's working.
Okay, there's 6 minutes now. Limit passed. Okay, we are very happy to introduce our today's speaker, who was our former member, Nilsson. He will talk about cosmological anisotropies and parity violation effect. Okay, start.
Right, let's see. Thank you very much for the introduction. And thank you for the invitation. Okay, I think we figured out how to use it. Another pointer? I don't know.
So we should provide a pointer.
Do I?
We don't.
I would settle for a stick.
Anything.
I can.
Yes.
Okay. Okay, we will try. Okay, so yes. Thank you very much for the invitation. And today I'm going to talk about some work with some people here in Korea, which is these two papers, one of which is in PU, one of which is under review, and then this paper, which is with a collaborator in France about cosmic birefringence, which was recently published in PRD. And let's see. Yes, okay. So we'll start with some introduction and some motivation. And in the first part of the talk, so that's number 1, 2, and 3, I'm interested in some way to study cosmological anisotropies. Something which is not cosmology, which is not with something which is not FLRW. And we will do that with some supergravity inspired, quote unquote, inspired model, which contains this dual interaction. And in the second part of the talk, I'll discuss some new results of cosmic birefringence, which is also consistent with this dual interaction and the electromagnetic zone. Okay. So we'll start with some nice pictures. And this is the universe. So this is from the WMAP team. This picture credited to WMAP. And it shows you that the universe is almost exactly homogeneous and isotropic. All the way back to, I don't know if I can draw on my own, yeah, I can. All the way back to the cosmic microwave background. But I will show in the last part of the talk that maybe there is a signal of parity-violation in the CMB, which accumulates as the photons travel to the Planck observatory. So what I'm getting at here is that there's something missing from the standard cosmological model, which normally is cooked up in this way. There is some ordinary matter, which is maybe a few percent. There's some cold dark matter. There's some cosmological constant, which somehow is the major ingredient. And then the universe is also expanding, and the cosmological principle says that the Copernican principle says that the universe is homogeneous and isotropic on large scales. So, which seems to also fit with the cosmic noise theorem. Okay, so at least locally, at very low redshift, I want my model to be approximately homogeneous anisotropic, up to some small corrections. What I'm saying here is that it's homogeneous anisotropic on large scales. And what does a large scale mean? It means something like 100 megaparsecs. And 100 megaparsecs is in redshift space is almost nothing. So according to the Planck mission, the temperature maps of the CMB is completely isotropic up to some 10 to the minus 5 fluctuation in the time across the whole sky. And baryon acoustic oscillations seem to vindicate, seem to agree with this. And the low scale distributed galaxies are more or less isotropic. And these large scale simulations of the cosmic web seem to also, the Millennium simulation, for example, seem to agree with lambda CDM prediction. So it seems to be homogeneous and isotropic on large scales. However, there are some burrs in the blanket, and I've just picked a few. This is a review which goes into detail of almost everything. There seems to be some weird alignments in the CMB, where the CMB portable and optical are mysteriously pointing in the same direction. There's some anomalous bulk flow, where the groups of galaxies seem to be moving in the same direction. Some kinematic effects that cannot be easily attributed to the kinetic dipole in the CMB, the peculiar velocity of the galaxy with respect to the cosmic flow. There are some dipoles in radio galaxies, and there's some interesting work on variation of the fine structure constant in different positions of the sky by John Webb's group in the UK, where they have been working on this for decades now, and they claim to find.
You mean that besides bounds, there are also some kind of indication?
There are small, very small indications. I don't know exactly what the level is, but it's small but significant. And I highlighted the recent results on cosmic private fringes, which seems to indicate that there's some parity-violating interaction present in CMB radiation. So there are some issues, and if you plot these issues on the sky, there seem to be a few points of contention on the sky. Here is the quadrupole-octupole alignment, and it seems there are some groups that claim that you have higher values of the Hubble constant in some
This is
positions.
so-called axis of value.
Sorry,
This is the so-called axis of value.
maybe they call it this.
I don't know. That some people think.
I don't know. This is okay. So there's also the Hubble tension, which I think everybody knows. There's a 5. It's more than 5. It's 5.4 sigma discrepancy in the measurements of the Hubble constant. When you compare late time supernova, this inverse distance ladder measurements to the measurements by the CMB. So here we see something like 68, and here you see something like 73. And if you say that the curvature parameter in lambda CDM is not 0, you obtain things like this, 53 kilometers per second. That's to make a second. Kilometers per second per megaparsec. Yes.
Curvature parameter mean it's open or closed?
Sorry? This data point prefers a closed unit.
Closed.
Yes, omega k less than 0. Which we can see here. And I believe that it is this, I think it's this one, I'm not completely sure. But it's actually this paper by Eleonora Di Valentino and et al. where they claim.
So you're saying bubble tension is also related to anisotropy, or I didn't?
No, not necessarily.
Yeah.
Not necessarily. I'm just pointing out that there are some issues in lambda CDM. And so there are some hints that things are not quite right. And then just like a month ago, Desi produced these very nice results, which seems to show that dark energy is 3.6 sigma away from a cosmological constant, which is exactly this discrepancy here. It seems to be, we seem to have a equation of state for dark energy that's evolving and absolutely not equal to -1. They do this. This is done by combining data sets. It should be mentioned. This CBAO on its own is this dotted black line here, and then it's combined in different ways, and especially when you include the Pantheon plus supernova catalog, is when you get the strongest constraint, which is a 3.6 sigma deviation from pure cosmological constant. Or I think maybe it was 3.4. Time dependent, yeah. Or actually, this is the CPL parameterization, so it's depending on the scale.
More earlier stage is more higher than.
WA is negative, so you write W as W0 plus WA.
Yeah.
Z minus.
Yeah. You
A means
Is the linear term
W0 plus
plus
WA multiplied by 1 minus the scale factor. This is the CPL
Minus
parameterization. A.
so it's negative.
Yeah,
WA,
yeah.
so
This is the first two terms in a Taylor expansion of the
it
equation.
works.
It gets worse, yeah. But this is what this is claiming.
So cosmological constant is bigger in the part. Or this is equation of state.
This is a question of state for dark energy. Okay, and then
what's the conclusion of that observation again? So it's
that the equation of state for dark energy is not a constant.
not
Constant. It's time dependent, and so W0 is the value today.
almost 0.8 or
Yeah, minus 0.8, depending on the combination of data sets. And WA is the characterizes the evolution, proportional to the scale factor, or 1 over h. Okay. So then there's cosmic parity-violation, which is a series of papers by Eiichiro Komatsu and his group in Germany, where I will go into this in detail later, but in standard electromagnetism, there is no so-called cosmic birefringence angle, and this is proportional to the mixing between E modes and B modes in the CMB, and this is a parity odd interaction. And by doing some clever analysis, they claim now that there's beta is not 0, and the significance level is 3.6 sigma, and it is consistent with this kind of axion photon coupling with the dual term, like a transinus term. Okay, so this kind of dual term seems to exist in the electromagnetic sector if we believe these results. So if it exists in the photon sector, why not in other places too? And how does it influence cosmological evolution? Okay. And how, if it does influence the cosmological evolution, can we somehow tie it to these small problems in lambda CDM? With the constraint that at least the local universe should be almost exactly. Okay, so one place where this kind of shows up naturally is in this kind of, I say inspired in some quotation, supergravity. So there's a pseudoscalar in blue. There's a standard Maxwell term, and then there's this dual interaction. And in what follows, this F mu is not necessarily the electromagnetic sector. It can be some new dark sector, or if it is the electromagnetic sector, then there'll be further very strong constraints from the primordial magnetic fields, etc. Okay, so if you can get the equations of motion from this. In these following slides, I will show the equations of motion for the case of an abelian gauge field. And I will compare it later on with a non-abelian gauge field, but the equations are horrifying. And so we can look at the U1 and we can look at plots of SU2. Okay, so just the equations of motion. It looks like this. And you'll notice that there is no, so I will just go back one slide actually. So this theta here is the coupling constant. And so if we follow the coupling constant, we see that theta does not show up in the Einstein equations. This is because it's the U1 case, and this dual term is independent of the measure.
So are those SPF?
Oh, right. Good question. This is the matter stress energy interaction, which we add as a perfect fluid, hence the TF index. Okay. In fact, it only shows up here, and you have it split down here. Okay, so something should happen in the to the CL psi and to the new gauge field. Okay, and I want to also connect this somehow to cosmological anisotropies. So what kind of geometry should we pick? Thinking of anomalous bulk flows, it seems like there is some axis where things are flowing along. Okay.
So, and then for the perfect fluid solution.
Yeah.
So you are taking that the phi equal to identically 0, and the F or U1 field is also identically 0, and only considering the fluctuation, or what is the part of the perfect?
Part of the perfect fluid are the standard cosmological fluids, like except the cosmological constant, which is still naked right here. And so we have a matter contribution with equation of state equals 0 and radiation.
But for the U1 field and the scalar field,
Yes.
pseudo scalar field phi,
Yes,
it is identically 0.
they are not identically 0.
The background,
No.
it's not.
In the background. I'm sorry, what do you mean?
So you have two terms, perfect fluid plus anisotropic terms.
Ah, right. Okay, I understand the question.
The perfect fluid background method or background solution.
Yes.
So in the background solution, you have non-trivial scalar, pseudo-scalar, and the non-trivial U1 background.
No.
No, it's identical to
Right.
only through the fluctuation.
Well, this is not a perturbation analysis. What we're saying is that there is a way to split the equations into an isotropic part and an anisotropic part. So everything proportional to either the new pseudoscalar or the new gauge field are collected into the stress energy tensor. And this is exactly the stress energy tensor for a perfect fluid. Exactly.
So I think the question was, at the end of the day, the solution that you're going to talk about, does it have a non-trivial value for phi and A? I think that was.
Yes, it does, for sure.
And inevitably, FIW method will be anisotropic, or what? It will not be a FIW.
It will not be FLOW. It will flow towards FLOW, but it will not be exactly FLOW.
I guess, and you will show the solution.
Absolutely.
No.
At least a sample of the solution. Will be a good days.
So what you say supergravity inspired action?
Yes.
Why?
Well, the there's no cosmological constant in supergravity, if I understand this right. But we know that we have something that looks kind of like a cosmological constant. So we add it to the action to have a real limit to lambda CDF. When you set all the new fields to 0, then there should be lambda CDF. Okay, so I want to choose a metric, right? This is what we were doing. And we choose a metric which has some symmetry x. Okay, and that's with when curvature is 0, then this is Bianchi 70, which has one extra killing vector, which is kind of like angular momentum. Okay, and I just hate this plot because it's nice to see that from this paper that they find also higher values, I think, of H0 in some direction. So we pick something which is not FLRW and has instead some symmetry axis. Okay, and then I want to somehow connect the new gauge fields to the metric functions, because I want my anisotropies to decay to nothing, and so I'd like to connect that to the dynamics of some field. And so what you can say is that I want this new gauge field to lie along the killing directions of the mesh. Okay.
So as for the figure in the previous page, where I see the previous page. So most of the regions are the decelerating, or so I did not understand the colors. It seems that the reddish color is the accelerating and the bluish color is the decelerating, or the other way.
Actually, this plot shows a significance level in color.
Oh, I'm sorry.
Yeah.
This is just how.
This is just this is the significance level. It's just for illustration on the philosophy of choosing the Bianchi 70. Okay, so I put by hand, or I align my gauge field along the killing directions, and you can do this, and we do some algebra, and what you find by doing that is that the new gauge field components can only be time dependent, because I still have a homogeneous metric, and I do this for F, and I do this for A, and we can skip these details, and I choose some gauge, which I'm allowed to do, and the exercise with the killing symmetries means that I can write the gauge field components in terms of some basis E, which now depends on the isotropic and anisotropic part of the state fact, alpha and beta. And so the final Einsatz is such, and now we have some extra scalars that parameterizes the gauge field, and they are phi1 and phi2. So,
excuse me. So for the gauge fields,
Yeah.
I mean, can you still have like a pure gauge part that's spatially dependent? Is that, I mean, for example, could you just impose the killing equation on FU only and not on AU? Would that give you something different?
I don't think that's possible. You can't have any, because if you have spatial derivatives in F mu, then they go away due to the killing directions.
Right. Okay, so requiring like.
So F and A are not independent.
Sorry?
F and A are not independent. Right.
Yeah. Okay, I was just wondering if there's any. So there's no flexibility there.
I don't think so. Either way, we didn't consider it. Okay, so I just you can choose this Ansatz. It's okay to do it using these assumptions, and you get the equation for motion in exploded in index values that look like this. And I just want to show them so you can see what's going on. This looks like a normal scalar field equation motion, except that there is some dependence on the anisotropic metric functions beta. The same thing happens. This is essentially the parameterization of the gauge field, where there's another. So here, and here, there's anisotropic.
So you said your potential depends on only time.
Only time.
Yeah. So you have only electric field.
Right. Yeah, actually, I haven't chosen the potential yet. I will choose it on the next slide. But you're correct. It's only time. And actually, in the perfect fluid part, there's also anisotropic contributions. But again, we can split this into an isotropic and an anisotropic. So I want to, in the end of the day, I want to solve this coupled system numerically, and so I need to represent it with some sets of scalars. So you can do this decomposition, and this is for Bianchi set at 0, which actually this decomposition comes from a special case of Bianchi 1. And what's interesting here is that you have this isotropic limit. Okay, and this has to hold. If you want isotropy to be fully restored, then sigma has to be 1 or -1. This psi field has to be 0, and you cannot have any evolution in the. If this holds, then you can redefine all your coordinates and everything is lambda CH, or everything is FLRW. And then we choose two potentials in the U1 case, which is the one I'm showing the equations of. It's a lambda phi 4. And in SU2, we chose some more axionic type potential, kind of like they do in these gaugeflation and axionic inflation models. Okay, so then what? Take a breath before we look at plots for 10 minutes. And so there is some coupled system of ODs, and I have to solve them somehow numerically. And so what we do here is we expand all these scalars into an isotropic and an anisotropic part, and we do an order by order solution. So this part should be lambda CDM plus some plus a superscalar and a gauge field, and this part should be small, and it should contain some anisotropic contributions. And so this is the isotropic part of the scale factor. So it should not have an anisotropic part. So this is just alpha 0. This is the anisotropic part of the scale factor, and it should not have an isotropic part. So it's everything. So epsilon is this bookkeeping parameter for anisotropy. If you set it to 0, then everything is FLRW, and so on. And because it's Bianchi 7, 0, beta 2 should be equal to B. Okay. When you do this, a small subset of the equations look like this. You have to also tackle all the off-diagonal terms, which form their own constraint equations. But actually, in the SU2 case, they are satisfied automatically, thanks to the color structure. But in here, this is the isotropic part, which we solve independently as a seed solution. And here are the anisotropic contributions. And right, so this is also the Friedmann equation. We have, of course, 5 more equations. And so the isotropic part, for example, this is so alpha dot here is the Hubble parameter, and here we also included the energy density for perfect fluid. Okay, so again, a small summary. There's an isotropic scale factor. This is alpha. So the scale factor is e to the 2 alpha, such that alpha dot is equal to 8/8. And you have this pseudoscalar anisotropic scale factors, and some other scalars which parameterize these gauges. Okay, and I also want some boundary conditions which I place more or less arbitrarily at 20 gigayears. So the reason I'm placing them at 20 gigayears is because I want a small amount of anisotropy to survive the day. And so we say everything should be almost exactly isotropic at 20 gigayears. Okay, so a subset of the numerical solutions. U1 should be on the left, SU2 should be on the right. So I'm trying to contrast what the SU2 effects are by showing more or less the same quantity side by side. But sometimes there are log plots on the left and linear plots on the right, so we'll be careful. And this, for example, is one of those cases. So here's an SU2, and this is the scale factor. And what we can see immediately is that there is a small difference between us, between lambda CDM and this model at the present time. Part of this is due to numerical limitations, which prohibited us from forcing the scale factor to be exactly 1 at the present time. But you can see that it's not just a rescaling problem. So in fact, it diverges, the scale factors diverge at further late times. However, in the SU2 case, now this is actually alpha instead of A, but they're related through the log. And here are 3 different values of this SU2 coupling constant theta. And so you can see that even with something like 10 to the 9 in natural units, which is why we have to choose such a big value, it's completely impossible to see the difference, to see the effects, I should say, of the SU2 problem. But that's only if you only look at the scale factor. The difference is there, we just have to find it. So these are the anisotropic metric functions. On the left is U1, on the right is SU2 for a lot of different values. All right, I should be here. Beta 1 is on the top, beta 2 is on the bottom, and there is almost, it looks like there's a perfect mirror symmetry, but there is not. The difference between the 2 functions are something like 10 to the minus 7 or 10 to the minus 6 maybe. And so it should be clear that they diverge at early times. So there's some point here where this assumption of anisotropy being small doesn't hold, and so we shouldn't trust the numerical solutions at too early times. But again, in the SU2 case, there's no way to really, just by looking at the functions, to distinguish between theta equals 0 or theta equals 10 to the 10. You can also look at the average Hubble parameter. The average Hubble parameter is the geometric mean of all the scale factors summed up. And so the average one is H bar. And there's a small difference, as you can see at early times. But in the SU2 case, again, it's hard to see any difference. There is, however, some way to plot this so that the differences show up. So this is a measure of the ratio between the average to the anisotropic scale factor multiplied by 10 to the 7. So at early times, the difference blows up, but still, it's something like 10 to the minus 7, right? Because it's almost unity. However, if you do the same in the SU2 case, you get these oscillations on the order of 10 to the minus 11. The oscillations, of course, is because you have an axionic potential. And the same thing happens in the beta case. Now, both of these are SU2, because I have to show both. And again, there is this approximate mirror symmetry between beta 1 and beta 2. But here also you see there's 10 to the minus 7. So anisotropies seem to be on kind of the same order of magnitude in both cases.
So when theta is 0,
Yeah.
do you still have a non-trivial electric field?
Yes, you just don't have the FF dual term.
Yeah, so non-trivial electric field is theta for instead of
Yeah.
anisotropic
Yes.
field. So theta term is not that crucial for anisotropic.
Not for anisotropy. Yes, you can still have them. In fact, in the U1 case, the effect is almost completely completely negligible. But in the SU2 case, you do see some differences. All right, the barotropic index of dark energy. Actually, on the left, this is total barotropic index or equation of state parameter. And at the present time, the difference is on the order of a few %. So there is some effect in the equation of state. On the right, again, is the SU2 case, where the difference is even smaller, unless you plot the ratio, and you can see that the difference is about 10 to the minus 6. And of course, the divergence is artificial. Now, what's maybe the most interesting, in my opinion, is the equation of state for the pseudoscalar. So this is all SU2, because there's no non-trivial behavior of a lambda 4 pi-4 potential. So this is the isotropic order of the scale, not the scale factor, the pseudoscalar axion, and it behaves according to the axionic potential. And things happen when you tune this at the isotropic order. Things happen when you tune the coupling constant. So something happens here for certain values of the coupling constant. So for theta equals 0, actually it explodes at t equals 0. But if you raise the value of theta, it does not explode. And you can plot the equation of state, which is this. This is for the isotropic order. And it oscillates between stiff matter and cosmological constant, except here. And why this is, I don't know. This is just what comes out of the numerical solutions. So it starts at stiff matter and it goes almost all the way down to radiation. In fact, it goes closer to radiation the higher you put the coupling constant theta. Okay. So what we've seen here is that you can somehow induce some cosmological anisotropies by coupling the metric function to a gauge. Everything seems to decay. I mean, we put in a fixed point by hand, but we've done so because the cosmic no-hat theorem should be respected. And at present time, the anisotropies, which are characterized by the anisotropic functions beta, are somewhere on the order of 10 to the minus 7, which is exactly what local measurements of quasars are telling us. So on an order of magnitude estimate with, for example, bulk flows in quasars, it's okay. But at early times, of course, everything blows. Okay. So another thing you can do with the dual term is measure cosmic power fringes. And this is somehow a parity-violating interaction. So yeah, it's based on this recent paper. And a few years ago, there was all these waves by Komatsu et al., who reanalyzed the Planck data to account for what's called the miscalibration angle in the instrument. And the tricky part is that such a signal of cosmic birefringence is completely degenerate with this exactly this miscalibration angle. Because I don't know what to write. They call the calibration angle alpha, and the cosmic birefringence angle is beta, and this is some beta prime. So a signal of cosmic birefringence can hide in the fact that we don't know exactly the miscalibration angle of the instrument. So in a series of papers, they, although I'm not an expert on this, they carefully did some kind of simultaneous determination of both alpha and beta by combining some data sets from Planck and WMAP, and this is above my head, but they claim a 3.6 sigma detection. Okay, so you can write the Maxwell equations like this. Again, here from the second set of Maxwell equations, you can write the dual equation of motion like this. And the Maxwell term is parity even, because b squared and e squared transform the same on the parity motion. But this is this is a parity odd term. Because if you change parity in here, b transforms with the minus sign and e transforms with plus. Okay, so let's add it to the action. Except it's a surface term, so it goes away. Okay. Okay, so that doesn't work. But if you have some coupling constant, which is not a, not a coupling constant, a coupling function, it's just exactly what you find in the Chern-Simons interaction. Okay, so this is some new theta. I'm just choosing the same theta, and you can integrate by parts, and you can find this. Okay, and this is exactly what was done to explain this cosmic birefringence signal in, for example, this paper. There's been a whole series where they tried to find a way to explain the signal without any new physics. Okay, and I will tell you in a second what the possible sources can be, and also why they've been ruled. So right now it sits at 3.6 sigma, roughly 0.35 degrees. And that means that in the time that the CMB photons travel from the last scattering surface to the Planck or WMAP instrument, there's a leakage of E modes into B modes, which is exactly what they call cosmic birefringence. And there are some things that can mimic such a signal, and these are the main culprits: foreground contamination like dust in the galactic plane. So the re-radiation of photons by dust can mimic cosmic birefringence. And okay, I don't know exactly which paper does what, but all the references are here. And they try a variety of galactic masks to remove all the foreground contamination, and the signal is still there. The signal is slightly weaker, slightly less statistically significant, but it's still there. Faraday rotation by primordial magnetic fields. This has been ruled out because great. Okay. Right. This has been also been ruled out.
Is that the prime time derivative?
In this case, it's conformal time. in this equation. Okay, fine, thanks. Yes, but if you try to generate with cosmic birefringence through Faraday rotation, you see that the angle in what we call theta prime here should be frequency dependent.
Part of the rotation is
Right, right. It's ruled out because it gives you a cosmic birefringence angle which is a function of the frequency, and there's no frequency dependence in the signal. Okay, so what they have found is that this is, well, as far as they can tell, consistent with an axion photon coupling. And this is interesting. But okay, so there's parity violation in the CMB according to this group. And what we realized soon after this came out was that not only you can actually generate exactly the same, you can actually get exactly the same term from the standard model extension with a CPT breaking contribution to the photon sector, which is exactly this term. And this is interesting because we have in our possession very strong constraints on so this KF is a derivative operator, and these KDF, I'm sorry, that was wrong. This KDAF is the CPT odd term, and there are very strong constraints on these from other photon experiments. Okay, so if I take the mass dimension 3 KAF hat term so that there are no more partial derivatives, then I can exactly re-obtain this transition term. And what happens is that you get this modified Ampere-Maxwell equation. This is the magnetic susceptibility tensor, and this is the spatial part of KAF. This is the temporal part of KAF. And this induces kind of a mixing matrix between the slope parameters. And so the Q and the U are the slope parameters which are related to the E and B modes, the parity eigenstates in the C and B. It's not the same as the electric and magnetic field. It's just something that, it's just a name. It's just something, so this is even under parity inversion, and this is all. And then it's all exploded by the spin-weighted spherical harmonics. Okay, so E is parity even when L is divisible by 2, and B transforms in the opposite way under parity inversion. And so you find that you can write the EB power spectrum, or the angular power spectrum, as some constant times the EE and BB spectrum. This is what happens. And the tilde here means that this is the standard case. So if you have the EE and BB spectrum in the standard case, you can find the EB spectrum. And this bar here means that this coefficient has been integrated from the last Gecking's simplicity. Okay. So this is my term from the CPT breaking term from the standard model extension, and this is what happens when you have an axion photon couple. So there is some similarity. Good. So actually, I think this should maybe be a factor of 2. Either way, you can easily just map these. And I then want to massage my KAF bar into something I can compare with other experiments. And this is exactly this term, which we call KV300, absolute value. Okay. I do this only because it's easier to compare with other experiments which also use the same notation. And before we had cosmic birefringence, the best constraints are exactly these, on the order of 10 to minus 44 GeV. From Planck, from Bicep 2, and from the Atacama telescope. But now let's assume that we believe that cosmic birefringence is real, and we use the cosmic birefringence angle and this relationship. Then
What is the eta?
sorry, conformal time. Conformal time.
So eta 0 is a minus infinity or something?
Cosmic.
Oh, at
sorry.
the time of the
Today. It's today.
Oh, 0 is of today and
LSS is the
okay.
surface of Alaska. That's right. Okay, so what you find is that using this is not the strongest constraint, but we use it because the strongest constraints uses a more sophisticated way of decoupling the miscalibration angle. And so this expression becomes much more complicated, and there's no easy analogy. So we use this one, which is non-zero 2.4 sigma, and I find this. So this is almost 1 order of magnitude stronger, but it's not only that, but at 1 sigma, it doesn't cover 0. So you have 2 points of reference. The fact is that you believe cosmic birefringence. So the cosmic birefringence angle is not 0.
So with that K value, or what would be the wavelength, or how much they will propagate after large scattering source? So is it possible for them to oscillate at least many times, or because it's very tiny?
It's very, very tiny.
So then I don't know. I mean, the universe is about 17 second or something. Is that the age of the universe? And I multiply there and the square. Since they don't have any chance to oscillate many times.
But the thing is that this is both beta and this KV3 is a cumulative effect.
That's right.
It's what you find after you integrate from the scattering surface to today.
And what is beta?
Beta is the cosmic birefringence angle, and from the axion photon coupling, it's
you put you just plug in as a heat.
If you plug it in, yeah. So this is strange. So not only this tells you that there's some CPT problem in the scene. Not only cosmic birefringence, but maybe a problem with CPT. There are, of course, many sources of error in here. I can think of one immediately, and it's this integral of over cosmic time or conformal time. Maybe there is a problem with the miscalibration angle with absorption. The Planck team claims that there is no signal of cosmic birefringence in their data. So this should be taken with a grain of salt. We already went through these other sources of rotation, which have been ruled out by the same team that claims the signal.
What you're saying is that this calibration signal means Komatsu's analysis is something wrong there? Or?
It could happen. It could happen. Because the miscalibration angle is completely degenerate with this beta prime. So if you're not completely sure of the miscalibration, you are probably overestimating the cosmic birefringence. Okay. Either way, this was included in our official data tables, where you can see how it relates to all the other constraints from photons on CPT and Lorentz violation. Okay, that's all. pretty much on time. So more than anything, this cosmic birefringence indicates that there is this FF dual term in the photon sector. And these type of terms show up in other places because why not? If they exist in photons, then they could exist somewhere else. And we tried to use one of the models to see what happens with cosmological anisotropies. And things explode at early times. This is unfortunately a consequence of setting initial conditions at late times. But the cosmic know-how theorem seems to be okay with it. And we were able to map this cosmic birefringence signal to give the strongest constraint that we have as yet on these CPT violating coefficients in this. So now they're in the data tables. Okay. Thank you very much.
So I just want to just check if I'm understanding the last part correctly. So the cosmic birefringence, this non-vanishing beta angle,
That's right.
implies the existence of this parity-violating term reaction.
That's right.
You said that is very similar to the CPT breaking term in the standard model.
It's an exact map.
The exact map.
Exact map.
So if that measurement of non-vanishing beta is true,
Yep.
we are implying that this CPT breaking term should be there.
Should be there. So it's also Lorentz breaking.
And that's why this K value is expected to be non-zero, even
Right.
if it's small.
Right.
That was the
That's
key.
right. So a caveat here is that you're measuring the absolute value, right? So
Yeah.
if I'm saying that the absolute value is between like 10 and 3, then essentially I'm covering 0. But I also know independently or semi-independently that beta is non-zero, and this is not an absolute value.
Is this the only source for explaining this non-vanishing beta angle? Is there any other chance for some non-CPT breaking term to explain the same beta angle, or in a way? I mean, if I wanted to say CPT,
If you want to say CPT,
and
then
then still is there a chance to produce that beta angle?
it's going to be hard. The group really tried. There were the big ones are galactic dust, like foreground contamination of the planet, which it changed they chose many different masks, and it did change the results, but the signal is still there, and it's still over what 2.5 sigma.
So I think CPT is invariant, right? We are not breaking CPT. But we are breaking parity or CP.
This is a CPT breaking signal if it's true.
CPT.
Yeah, because there's no C in the photon sector, but the way we classify these terms in the SME means
I thought, what is it?
CPT. So parity is broken.
Would be CPT, not the CP or parity? It's not enough.
Well, if P is broken but CP holds, then CPT is broken.
But both can be broken, and while keeping CPT okay.
If you break both, yes.
Yeah, I mean essentially the FF dual like terms, axionic terms, is not breaking CPT, right?
This term does. I mean this term is CPT odd in the EFT expand.
CPT
The CPT odd and local Lorentz breaking.
So I think the original extraction comments mentioned.
Yeah, the
That was
axiom.
just parity violation.
This is exactly parity violation.
But if you try to explain that in the extended standard model,
Yes.
you cannot help but add the CPT breaking term.
Exactly. This term gives you exactly the same effect. So it's indistinguishable, you could say, from a CPT violating interaction. Or at least from a parity violating local Lorentz breaking interaction. either way, the signal is indistinguishable from being produced by such a term.
Because it's EFT and then maybe some weird CPT breakdown could happen.
Yeah. But this is the only one the only CPT odd local Lorentz breaking term that can generate the same effect.
So does this include axionic like terms, or is a quite different realization?
Well, this one is axionic like, right?
Axionic like.
Yeah. This the mass dimension 3 one is axionic like. It has to be, yeah. Because then you cut these partial derivatives and you find a non, and this is not necessarily a constant. If it was a constant, then we could, then there would be no effect. Okay, but this has to be somehow independently tested with some other experiment, some other data.
And I guess we in that term in front we have if we realize that term in terms of axionic like terms,
Yeah.
we do need some non-vanishing pseudoscalar field, right? Kind of that term.
Yeah, that's
So that's why I guess your claim of CPT violating sounds to me a little bit big claim.
it is. This is why we hid this in the text in the paper, because we didn't want to say it very loudly. But it's okay, whether or not I'm claiming CPT violation, the constraint is real. The constraint on this term is real. We can for sure claim parity violation in the CM.
So once again, what is the major argument of that you concluded that it may be miscalibration angles? What is the major component?
The Planck team has a miscalibration angle and
It is consistent with the observation data. I thought it's a non-zero up to 3 sigma. Of course,
Right.
This is not enough yet,
Mhm.
but certainly you claim miscalibration.
Right. This is one source of such a signal is the miscalibration angle of the satellite itself. And this is why for example, Planck does not talk a lot about polarization of CMB photons because they're not completely sure of the miscalibration angle, which is degenerate with polarization effects. But what Komatsu et al. Did was take the raw data and they invented some method to determine beta and the miscalibration angle independently. And this is where these claims come from. That's it. But the Planck team claims that there's no signal.
What do you mean with foreground contamination?
Sorry?
Foreground contamination.
Yes, the dust in the galactic plane. The interaction of CMB photons with dust in the galactic plane can mimic the results. But
It's purely
yes, and it's ruled out, in fact. It changes the value of beta, depending on the mask you choose, but the signal is still there and significant.
Other questions?
Could you, so you have some the K wave vector, that number 10 to minus 45
Yeah.
GeV. So that's a dimension field.
Yes.
Are there some simple argument, that determines depth or magnitude?
What do you mean now?
So how do you get 10 to minus 45 GeV? I mean, I cannot follow the detail of your calculation.
Right, I've omitted some things, of course.
And what is the major important dimensionful parameter in the calculation that leads to that conclusion? So is it eta or?
This, we have eta, this is dimension full. This gamma is dimension full because you have c squared. And in the end, I left out the exact conversion ratio. But this gamma is dimension full.
Or to put it another way, any and wavelength, depending on the polarization, there are two polarization, right? So there will be more and more the rotated angle in the between EV modes, right?
Right.
So which will be proportional to the distance that
Yes.
they propagate.
Yes.
So in the far future, then the K, so K depends on the traveled length or?
Yeah. KV is, do I have it? Yes.
Then what is the meaning of K? So I thought every wavelength in principle, every wavelength, there may be some rotation angle.
K is not a wave vector.
Oh, what is
It's
K?
just a name.
Oh, it's a name.
K is,
That's a dimension of wavelength.
this here is KAF hat, and KAF
Essentially derivative.
hat is some coefficient in front of a bunch of partial derivatives. And so this one for mass dimension 3, so no partial derivative, exactly reproduces this thing, the EV spectrum, which is in clear analogy with what's created by an axion photon couple.
So right-hand side term in front of the parenthesis is dimensionless, while the left-hand side is a dimension. How
Yes.
can you compare those?
There is a conversion factor, which I have left out, and I
When it's EBK, the other is EB5, that's not the same thing.
cannot recall exactly what the conversion factor is, but it's in the paper. There is a way to, actually there's a paper by Caloni et al. 2022 in JCAP, where they actually do this in detail for these coefficients.
Because I mean, I worked with Nilsson and others last year on this issue.
Yes.
But they are accepting the Tomato's observation. And there are many different models, right?
Yes.
We saw that at least in a model independent way, we can just explain that kind of rotation.
Right. I saw
But
your
your result seems to be kind of somehow opposite conclusion.
Yes,
That,
but
maybe this alignment, maybe.
yes,
So that's why I'm.
it's the claim by